Looking at organic chemistry, and we're specifically going to look at aldehydes and ketones. So our learning intention is to explore the structure, nomenclature and properties of planar carbons, and in this video, as I said, we'll specifically focus on aldehydes and ketones. So when it comes to planar carbon compounds, it's important to discuss what planar is. So planar carbon compounds have a bond angle of 120 degrees between each of their bonds. So that's what planar means. And there's four types of planar compounds. There's aldehydes, ketones, carboxylic acids and esters. And in this video, we're going to focus on aldehydes and ketones. So to begin, let's look at aldehydes. And as you can see in the name, I've highlighted the H. So similar to the alcohols, this is going to have significance. Aldehydes have a functional group of CHO, where this is called a carbonyl group. So CHO is C double bond O with a H attached on. And then our carbon chain goes on this end here. It has a general formula, CnH2n plus 1, where N is the number of carbons. And it's handy to remember this general formula because if you're asked to name an aldehyde or construct an aldehyde, you can check that your answer is correct by filling into this formula here. The aldehyde functional group must always occur at the end of a carbon chain. So that's one key thing to look out for when you're doing aldehydes. The functional group, the C double bond OH, will be at the end of the carbon chain. So if you don't see this functional group at either end of your carbon chain, then you do not have an aldehyde. Now, when it comes to naming aldehydes, it's quite a similar process to what we would have taken for our hydrocarbons or for our alcohols that we've discussed already. And what you do is you identify the longest continuous carbon chain. And what you do is you change the ending of your parent alkane from E to Al. So that basically means that the E is taken off the end and it's replaced with an Al. Then you number your carbon chain such that the end with the functional group, which is C double bond OH, has the lowest possible number, and then indicate the position of any substituents and construct your aldehyde name. So here's a slide showing some of the basic aldehydes and their names and chemical formulas. So we've got methanol, which is HCHO, and that's it up here. Then we've got ethanol, which is CH3CHO, and that is this one here. Propanol then, C2H5CHO, is here. And then butanol, C3H7CHO, is there. So as you can see, the CHO is common with all of these names and chemical formulas. So the CHO is the functional group, and attached to it then is either a hydrogen or an alkyl chain. So let's try an example of how to name a more complex aldehyde. So as we can see here, I have an aldehyde, and the first thing we need to do is we need to count the longest continuous carbon chain. Now I can see here 1, 2, 3, 4, and there is a fifth one here. It's disguised to make it look like it's a substituent, but it's still a carbon that's directly attached, so it is part of the longest carbon chain. So that's 1, 2, 3, 4, 5. So that means I have 5 carbons, so that means I'm going for propane, but I know that this isn't an alkane, it's an aldehyde, as indicated by my functional group here. So I know that that name will actually be propanol. So that is step 1 and step 2 completed. Step 3 is to number our carbon chain such that the functional group has the lowest possible value. So that's 1, 2, 3, 4, 5. So I've that done. I have to indicate any substituents. So I know that there's a substituent of a chloro. So that will be 2-chloro. I have a bromo, so that will be 3-bromo, and they are all of my substituents. So now I have everything done that I can assemble the name. Now it's important to remember that we assemble alphabetically, so it will be 3-bromo, 2-chloro, and sometimes that throws people off because the 3 is coming before the 2, but what you have to remember is that you're labeling and assembling the name alphabetically, so bromo and followed by chloro because B comes before C, so it's 3-bromo, 2-chloro, propanal, and that is that structure labeled. So let's look at the physical properties now of aldehydes. So aldehydes are liquids apart from methanol, which is a gas at room temperature, but all other aldehydes are liquids. When it comes to boiling points, aldehydes have higher boiling points than their corresponding alkanes, and that's due to the polar carbon-oxygen double bond here, causing a permanent dipole-dipole interaction between aldehyde molecules. And that's coming from the electronegative oxygen pulling the electron density towards itself to give it this partial negative charge and resulting in the carbon having a partial positive charge. However, it's worthwhile noting that aldehydes do have lower boiling points than alcohols, and that's due to the difference between dipole interactions and hydrogen bonds from the bonding chapter. So when we look at solubility, short-chain aldehydes are soluble in water, and that's due to the polar carbonyl group that's present, the polar C double bond O group, and the oxygen atom on the carbonyl can actually undergo hydrogen bonding with a hydrogen atom of the water. So that's what makes it soluble, where the oxygen of the carbonyl can undergo hydrogen bonding with the hydrogen atom of water. Now, similar to our alcohols, there is a trend as our alkyl chains get longer in aldehydes. So as the number of carbon atoms increases, solubility in water decreases, and this is due to the increasing size of the non-polar part of the aldehyde. So there is more non-polar carbons present than there is for your carbonyl, so it won't dissolve in the water. So solubility increases in cyclohexane as your carbon chain gets longer in an aldehyde. A unique aldehyde to look at is benzaldehyde, and benzaldehyde has this structure here at the top where we have a that's representing a carbon, and then each point on our corner of our hexagon in benzene represents a carbon also. So benzaldehyde is an aromatic aldehyde, and it's found in almond kernels, and it's used for flavouring in cooking. So let's move on to ketones. So ketones have a functional group of C double bond O, and they have a general formula of OR-CO OR-dashed, and OR and OR-dashed are literally just alkyl groups or alkyl chains, so chains of carbon atoms basically. The only structural difference between an aldehyde and a ketone is the replacement of the hydrogen atom in the aldehydes by an alkyl group in the ketones. When you're looking for a ketone, it is key to remember that your functional group will be in the middle of your carbon chain. So it won't be at the end like the aldehyde, it will be in the middle of the carbon chain. When it comes to naming ketones, very similar approach to the aldehydes. Identify the longest continuous chain of carbon atoms. Change the ending of the parent alkane, so you remove the E and you add -one or 1 for ketone. Number the carbon chain starting from the end that gives the C double bond O the lowest possible number, and then indicate the position of any of your substituents. So here's two very common ketones. We've got propanone here, which is commonly called acetone, and then we have butanone. So here's an example for us to work with. So step one is to identify your longest carbon chain, and I can see here that it is 1, 2, 3, 4. So there's 4 carbons in my longest carbon chain, so I would know that that is going to be propane if it was an alkane. However, I know that I remove the E from the end, and that becomes propanone. So that's step 1 and step 2 completed together. So step 3, we need to number our carbon chain such that our C double bond O has the lowest possible number. So there's 2 ways that we can label it. We can go left to right, or you can go from right to left. And I can clearly see that the numbering on the top here has our carbonyl group on carbon 3, where on the bottom it's labelled as carbon number 2. So I know to use carbon number 2, so it's the bottoming numbering that is correct. So that gives me propan-2-one. Step 4 then indicates the location of any substituents. So I can see that I have one substituent, and it's a chlorine, and it is on carbon 1, so that is 1-chloro. And step 5 then will be to assemble alphabetically. So I know it's going to be 1-chloro propan-2-one. And that's it labelled. So let's look at our physical properties of ketones. So butanone and propanone are liquids at room temperature. When we look at their boiling points, we can see that ketones have higher boiling points than alkanes, and this is due to the polar carbonyl group, the C double bond O, causing permanent dipole-dipole interactions between ketone molecules. So this reason is exactly the same as the reason we had for our aldehydes. However, the boiling point of our ketones is lower than that of our alcohols, and that's due to the fact that there is no hydrogen bonding present between ketones. Short chain ketones such as propanone, they are soluble in water, and that is due to, again, the polar carbonyl group, and the oxygen atom of the carbonyl can undergo hydrogen bonding with the hydrogen atom in the water molecule. So that is again similar to what we would have said for the aldehydes. So the longer the chain, the less soluble our ketone is in water. And finally, a use of propanone is a solvent, and it's actually used in nail varnish remover. So that's it for today's video. Have a read over the learning intentions to make sure you understand everything.